on numerical methods in civil engineering, we will talk about solving multidimensional nonlinear equations. In the last lecture, we focused, and the last two lectures, we focused on 1D nonlinear equations, and we looked at the methods of solution, various algorithms for solving those equations. We looked at the convergence properties, when those algorithms are going to converge, and we also looked at the order of convergence of those algorithms, the rate at which they are going to converge. So, this time we are going to focus on multidimensional nonlinear equations, and we will see that many of the techniques, many of the algorithms we looked at for 1D nonlinear equations, they carry over to multidimensional nonlinear equations in a more general form. So, let us consider a system of n nonlinear equations in n unknowns. We have n equations. So, a sample equation is like this: f I for I is equal to 1. So, there will be f1, f2, f3 and so on up to fn. There will be n equations, and each equation is in n unknowns. So, then we have a system of n equations in n unknowns, f1, f2, 3, f3 up to fn, and my variables are x1 through xn. A one-point iteration method for this equation can be constructed by rewriting this system like this. We saw for the 1D nonlinear equation how we can rewrite f(x) equal to 0 to x is equal to f(x). If we can write that, we can construct an iterative scheme. Similarly, in multi-dimensions, we construct a series of equations, n equations in fact. x1 is equal to phi 1 of x1, x2 through xn, x2 is equal to phi 2 of x1 to xn, and so on and so forth. So, again the same n equations, we are just rewriting them as xi is equal to phi I of x1 through xn. Once we do that, we can use the iterative method, right. But now, instead of having an iterative method for one equation, we have an iterative method for n equations and n unknowns. So, that iterative method will be like this: xi at k plus 1. So, my new value of x is equal to phi I, that function evaluated with my old values of x, and I keep on iterating until it converges. So, we introduce vector notation. We have this vector x, which basically means x1, x2 through xn. This should not be in bold, right, because x1, x2, xn are scalars, right. So, vector x is a vector while these are scalars, while phi of x, that is a vector, and that comprises these scalars, phi 1, which is a scalar valued vector function. So, it is a function of a vector x, but its value is a scalar. So, it is a scalar valued function of a vector, right. So, phi 1 of x, phi 2 of x, phi n of x, these are my phi's, and then we have in vector notation I can write the iterative scheme as x k plus 1 is equal to phi of x of k, right. So, we have n equations like this, right, n equations like this, x1, x2 and so on and so forth, and this is going to hold for k equal to 1, 0 to n. So, similar to the convergence criteria for a generalized iterative algorithm, we can construct a convergence criteria for multidimensional nonlinear equations also. So, let us suppose that alpha is the converged value for the iterative scheme, that is alpha is equal to phi of alpha. So, once it converges, phi of alpha is equal to alpha. So, that is my root, right, and f of alpha is equal to 0 because that is my root 2, right. So, let us define a matrix. So, when we looked at the 1D Newton-Raphson for 1D nonlinear equations, we looked at the derivative of phi with respect to x, right, one variable, but now we have multiple phi's and we have multiple x's, right. So, we are going to have a matrix of partial derivatives, and what will be the terms in the matrix like del phi 1 del x1, del phi 1 del x2 and so on and so forth. So, the first row will be the derivative, partial derivatives of phi 1, with respect to x1 through xn. The second row will be partial derivatives of phi 2 with respect to x1 through xn, and so on and so forth. So, it will be a n by n matrix if I have n phis and n x's, right. And this matrix typically is known as the Jacobian matrix. It is the Jacobian matrix, and so let us suppose that each of the partial so now let us look at convergence of nonlinear systems. We looked at convergence of linear systems, and we found during the convergence of nonlinear equations of one variable, and there we found that if in a neighborhood close to the root we impose certain conditions on my derivatives, the derivatives are bounded, right. We said the derivatives are bounded in a neighborhood of the root, and in that case we can show that if we start with an iterate in that neighborhood, then we are going to converge to the root, right, and we are going to always stay within that neighborhood. We are not going to leave that neighborhood, and we are going to converge to the root of to the solution, right. So, similarly, let us suppose that each of the partial derivatives, so each of the partial derivatives in my Jacobian they exist in a neighborhood of the root, right. And that neighborhood I am calling R, right. And how am I defining that neighborhood? That neighborhood is R such that x any of my solution candidate solutions, right, is within a sphere, within a hypersphere. Actually it is not a sphere because this is n dimensional space, right, within a hypersphere whose center is at the root alpha, right, n dimensional vector with center at n dimensional vector alpha, and then I have a hypersphere centered at alpha with a radius which is rho, right. And I am saying that I am looking at all those x's which lie in that R, in that neighborhood of the root, right, and I am imposing the condition that each of the partial derivatives exist, all those partial derivatives del phi I, del x j, they exist in that neighborhood. Then a sufficient condition for the iteration method to converge for every x0 belonging to R is that for some matrix norm, the norm of the Jacobian matrix must be less than m, where m is a number which is less than 1, right. So, the criteria is that Jacobian matrix, and then I evaluate the norm of that Jacobian matrix. We looked at several definitions of matrix norms, right. We looked at several definitions of matrix norm earlier in the course. Suppose we take one of those norms, for instance the infinite norm, right, or maybe the L2 norm, right, any of those norms, any norm, so long in some consistent norm. It says nothing about the type of the norm, right. If in any norm this is less than m, which is less than 1 for all the x belonging to R. So, this norm of the Jacobian matrix is less than 1, is strictly less than 1, then we are going to get convergence. That is a sufficient condition for convergence. Let us recall that for the iterative scheme, we have one dimensional nonlinear equation in a single unknown. The sufficient condition for convergence was norm of phi prime of x is less than m less than 1. So, this is just a generalization, right. So, instead of a mod here, I now have a matrix norm, right. I have a matrix norm, and this matrix norm must be less than 1. Okay. Hence, the parallel is clear. Using the mean value theorem in multi dimensions for x and y belonging to R. So, we looked at the mean value theorem in 1D earlier on. So, now we are looking at the mean value theorem in multiple n dimensions, right, and we say using that mean value theorem, and for any x and y which belong to my little neighborhood R centered around alpha and with radius rho, I can write phi x minus phi y is equal to j of xi times x minus y. Recall the parallel. What was the parallel? It was phi of x, small x, where x is a scalar, minus phi of y is equal to del phi del x evaluated at xi times x minus y, right. So, that was my 1D mean value theorem. So, this is my multidimensional mean value theorem, where this is now a vector, that is a vector valued function of a vector, that is a matrix, and that is again a vector, right. And what is xi? Xi must belong to that space, because of the mean value theorem. Xi must lie between x and y, right. So, xi must belong, since both x and y belong to R, and since xi must lie between x and y, xi also has to belong to R, right. And how do we define xi? Xi is equal to x plus alpha times y minus x, where alpha belongs to 0, 1. So, I am drawing a, you can think of it in 3D if it helps to understand, right. I am drawing a vector from x to y, right, and my xi, my vector xi lies somewhere on that line, right. So, it is x plus alpha, some scalar, times the vector between x and y, right. So, that is my xi, right. So, taking the norm of both sides, again we can take any norm, right. For instance, let us suppose we take the infinite norm, right, infinite norm on both sides. So, norm of phi x minus phi of y is going to be lesser than or equal to norm of Jacobian evaluated at xi times norm of x minus y, right. We have seen that before many times. But we have seen that the condition for convergence is norm of j of xi is less than m, right, and we have seen that this is true, right. So, since this is lesser than, since xi belongs to R, this must be lesser than or equal to m, since norm of j of xi is less than m, right. So, this must be lesser than or equal to m times norm of x minus y. Thus, we can say that norm of phi of x is actually, it is not really norm of phi of x is a contraction mapping. Why is it a contraction mapping? Well, let us take a look. What it does is that if I have x and y, if I have two members belonging to that neighborhood, 2 points, two vectors, or let's think of it as points which belong to that neighborhood of R, centered at alpha. So, if I operate with phi on x and if I operate with phi on y, then the norm of phi x minus phi y, we can think of the norm as the distance. Norm is always like some sort of distance, right. So, the norm of phi x minus phi y is lesser than or equal to m, remember m is less than 1, right. So, it is less than the distance between x and y in the same norm, right. So, it originally I had points x and y. So, if I look at the distance between x and y, norm is like, you can think of norm like a distance. I compute the distance between x and y. Then I operate on x with phi, I get phi of x. I operate on y with phi, I get phi of y. And then after that transformation, I compute again the distance between the results of the transformation. And I see that after my transformation, the distance between those things is actually less than my original distance, right. So, it is a contraction mapping. So, the distance is becoming smaller, right. Distance of the mapped variable is smaller than my original variable. So, that is a contraction mapping. Since the norm of the vector between the mapped values phi of x minus phi of y is strictly smaller than the norm of the vector between the original values x and y, right. So, that is why it is a contraction. A necessary condition for x k plus 1 is equal to phi of x k, that is this iteration algorithm, to converge is that the spectral radius of Jx, the spectral radius, what is the spectral? That is the largest eigenvalue, right. The largest eigenvalue of Jx for any x belonging to R, for any x belonging to our neighborhood centered at alpha with radius rho is less than or equal to 1. Well, we can see this like, we can prove this as follows. Let's write xn plus 1 minus alpha. n plus 1th value of the iterate minus my root. So, x n plus 1 is equal to phi of x m, alpha is equal to phi of alpha because alpha is the root, right. So, phi of x n minus phi of alpha, again let us use our mean value theorem, and we can write j of xi is equal to x n minus alpha, where xi is equal to now x n plus h times alpha minus x n, h belongs to 0 and 1, and this I can write as lambda n times x n minus alpha, where lambda is n is an eigenvalue of j xi, right. So, this is just a statement of the standard statement of the eigenvalue problem. This is the matrix, that is my sort of eigenvector, that is my eigenvector, and that is my eigenvalue, right. So, that is an eigenvalue. So, I can write this like this, right. So, what do we have? We have x n plus 1 minus alpha is equal to lambda n times x n minus alpha, right. So, we had x n minus alpha. So, I can write x n as phi of x n minus 1, right, phi of x n minus 1 minus alpha, and we have done this so many times, this should be familiar to you now. So, now I can write lambda n phi of x n minus alpha, I will again use the same mean value theorem. So, I can write this as j of xi 1 times x n minus alpha, right, where now xi 1 belongs to the interval between x n minus 1 and alpha. So, again x n minus 1 plus h times alpha minus x n minus 1, h belongs to 0 1. So, now this again can be, if I write it as an I can write it in terms of eigenvalues and eigenvectors. So, the j of xi 1 times x n minus 1 minus alpha, that becomes lambda n minus 1 x n minus 1 alpha, where lambda n minus 1 is an eigenvalue of j xi 1 and x n minus alpha is. So, now I have lambda n minus 1 x n minus 1 alpha, where lambda n minus 1 is an eigenvalue of this. So, continuing this process, again I am going to write x n minus 1 as phi of x n minus 2 minus alpha. Again I am going to use the mean value theorem. I am going to write it in terms of eigenvalues and eigenvectors. So, eventually we are going to get lambda n minus 1, lambda n minus 2 through lambda 0 times x 0 minus alpha, right, which is my initial iterate, right, my initial guess to the value of the root. So, this is what I get. Then I take the norm of both sides. I get lambda, the absolute value of these eigenvalues, right, and I have norm of x 0 minus alpha, right, and this is always going to be less than the maximum of those eigenvalues, right. So, I look at each, this is like I am looking at all those iterations, right. So, I look at the maximum eigenvalue of each iteration, right, and that maximum eigenvalue over all the iterations, if I replace that here, right, I am sorry, this should be a power n, right, I am so sorry, this should be n, right, and this is norm of x 0 minus alpha, right. So, this time this to the power n times this is going to be greater than or equal to that, right. So, thus it is clear that the iteration scheme is going to converge only if mod of lambda max, the largest of the maximum eigenvalues of each of the j matrices j xi, j xi 1, j xi n is less than 1, right. So, the maximum of each maximum eigenvalue of this matrix, and then the maximum of those, right, maximum of all those must be less than, if that is less than 1, then we are going to get convergence, right. So, what does this mean? That means that the spectral radius of j x for x belonging to R, because this is going to be true for all these xi's, right, and only what is common between xi, xi 1, xi 2, xi 3 and xi n, they all belong to R, right, they all belong to R. So, they can be anywhere in R, right. So, that means that for this to converge, for any point x belonging to R, j of x must have maximum eigenvalue less than 1, right. Is that clear? So, that is going to be true if the spectral radius of j of x is less than 1. So, that was our convergence criteria. Let us take a look at the rate of convergence, right. You remember we looked at the rate of convergence for the one dimensional nonlinear equations, right, Newton-Raphson, secant, and so on and so forth. So, what can we say about the rate of convergence of this? The rate of convergence depends linearly on m, where norm of g of x is less than m less than 1 for all x belonging to R. How can we see this? Well, let us take a look. So, norm of x k plus 1 minus alpha, I can write as norm of phi of x k minus phi of alpha, which is equal to lesser than or equal to m times norm of x k minus alpha. We showed that earlier on, right. Let us take a look at that again. From this, right, we showed that earlier, right. So, this is going to be lesser than or equal to norm of x k minus alpha. What is this? It is epsilon k plus 1. It is the error at the k plus 1th iteration, right, because it is the value of the iterate minus the value of the iterate at k plus 1 minus the root at minus the root. Similarly, this is the error at k, because it is the value of the iterate minus the root. So, we have epsilon k plus 1 is lesser than or equal to m times epsilon k. So, whatever is the value of m, that is going to govern my convergence. So, that was that. So, now let us look at, so that was our general iteration scheme, right, for phi of x, x is equal to x, right. So, now often we, instead of having phi x is equal to phi of x, we have, because of the physics, we are modeling, after all, in civil engineering or any engineering, we do not solve equations for the sake of solving equations, we are trying to model physical phenomena, right. And it may so happen that my physical phenomena gives me an equation like this, right, x is equal to a plus h of phi of x instead of x is equal to phi of x, where a is a constant vector and h is a scalar such that h is greater than or equal to 0, greater than 0 and less than 1. We can very easily put this system into a standard form. How do we do that? Well, to put it in the standard form, we define phi 1, which is equal to a plus h of phi of x, and write the iteration scheme as x n plus 1 is equal to phi 1 of x n. It is clear that if j corresponding to this, corresponding to phi, satisfies the convergence requirement norm of j lesser than or equal to m less than 1 for all x belonging to R, then j 1, which actually corresponds to that, is also going to satisfy that requirement. How? Well, j 1 is equal to norm of, well, norm of j 1, it is not j 1, I am sorry, norm of j 1 is equal to norm of del phi 1 del x, right, which is equal to, if we look at this, right, what is norm of del phi 1 del x is nothing but h times norm of del phi del x, right, and this is going to be h times norm of j, and since this is less than 1, then the iteration algorithm for this is also going to converge, because norm of j 1 is also going to be less than 1, right. So, if norm of j is less than 1, norm of j 1 is also going to be less than 1, and the modified algorithm is also going to converge. So, in case of simple transformations, simple, I mean, it is a slightly different iterative scheme, that also we are guaranteed is going to converge, provided that this condition is satisfied, right. Okay. So, up till now we talked about general algorithms, right, general algorithms, and we talked about general convergence characteristics, convergence requirements, rates of convergence. Let us become slightly more specific and look at certain specific algorithms, right. So, the first algorithm we will look at will be Newton-Raphson, right, because that is the most commonly used algorithm, most widely used algorithm, most versatile. So, up till now, and let us, so the Newton-Raphson method, in order to do that, in order to look at it in greater detail, what we need to do is to see how we get it in multi dimensions, right. and to see how we get it in multi dimensions, let us try to expand this function f of x, which remember is now a vector, right. It is a f1, it is basically f1, f2, f3, fn, and it is a function of x1, x2, x3, xm, and let us expand it in multi dimensional Taylor series, right, and let us do that. So, f of x is equal to f of x k. So, I am expanding it about at my iterate at step k. So, f of x k plus f prime evaluated at x k plus x minus x k plus the correction term, the remainder term, the higher order term, which is going to be quadratic and higher, right. So, this is my Taylor series expansion, and this leads to the n dimensional Newton-Raphson method, where the new iterate xn plus 1 is the root of the linearized equation. Remember, how did we get our Newton-Raphson method in 1 dimensions? We linearized it. We used the Taylor series expansion, but then we cut it off before the quadratic term, right. We kept only the up to the linear term. So, we linearized our expression, right, and that led us to the Newton-Raphson algorithm. So, let us do the same thing in multi dimensions. So, what do? We say that f of x k plus 1 is equal to f of x k plus f prime x, this we already saw, and we say that my new iterate x k plus 1. So, remember what we did in one dimensional Newton-Raphson. We took the tangent to my curve at the point and said, what is my new iterate? My new iterate is where my tangent intersects the x axis, right. What does that mean? That means that the function value, I am assuming that the function value is 0, right, because it is intersecting it has got ordinate 0, it is intersecting the x axis, right. So, what I am saying is that my x k plus 1, f of x k plus 1 is equal to 0, because that is where it is intersecting my x axis, right. So, it is just the parallel to that, right. So, my new iterate, I find it like this, right. So, f of x k plus 1. So, at x k plus 1, add the new value of my iterate, right. New value of my iterate, remember in 1D was it where it intersected the x axis, right. When would it intersect? When would a function intersect an x axis, right? When the function value is 0, right. So, similarly here, so I am assuming that the function value is 0, right. So, in that case this becomes 0, and I can write x k plus 1 minus x k is equal to this. Now, remember this is a matrix, right, this is Jacobian matrix. So, this inverse times f of x k, right. So, that gives me my new iterate x k plus 1, right. So, same thing, generalized, same idea, I have extended it to multi dimensions, right. So, the assumption is that x k, so the assumption is that if I take a point, right, if I take a point on my solution and I draw my tangent, right, and I draw my tangent and assume that that is a root of that equation, right, that is f of x k plus 1 is equal to 0, right. In that case, that gives me my new iterate according to Newton's method, right. So, the solution of this above system is not straightforward at all, right, and we shall look into the details of the solution procedure later, right. But one thing to note is that evaluating these partial derivatives. So, what does Newton's algorithm in multi dimensions require? It means that at every iteration I have to evaluate that n by n matrix of partial derivatives, right. And not only do I have to evaluate it, I have to invert it also, right. So, that the evaluation of the derivative is expensive, right. So, as an alternative to evaluating the partial derivatives of the function f, actually evaluating the partial derivatives, we can estimate the partial derivatives, right. How do we do that? Well, let us take a look. This can be done in the same way as this. Remember, we looked at the secant method in 1D, and when we started looking at the secant method, we started with the Newton-Raphson method and said that the secant method comes about if we, instead of evaluating the actual derivative, we we construct an approximation to the derivative, right. We construct an approximation to the derivative, and how do we construct the approximation to the derivative? By evaluating the function value at 2 points and dividing it by the distance between those 2 points, right. So, that is an approximation to my derivative. So, we are going to do the same thing in case of multi-dimensions, but in this case we are going to approximate each of those little partial derivatives in my Jacobian matrix. And how am I going to do that? Well, I am going to say that my del phi del xj, my partial derivative of function fi with respect to my independent variable xj, I can say that is approximately equal to fi x plus hj times ej, right. What is ej? Ej is nothing but the unit vector in the jth direction. So, if you think of in 3D, right, if we are looking at f3, right, it is x plus h3 times e3. So, it has got e3 has got 0 in first two terms 0, the last one is 1, right. So, it is the h, it is an increment in the zth component of my vector, right. If I think of an n dimensional vector, since this is an n dimensional space, if I think of an n dimensional vector, I am looking at an increment in the nth component of that vector, right, in the nth component of that vector. And what is the magnitude of that increment? The magnitude of that increment is hn. If I look at the jth component of the vector, so every other component is 0 except the jth component. So, it is a unit vector in the jth unit vector in my n dimensional space, right, and that jth unit vector I am scaling it with a value hj, right. So, I am taking a, one can think of it like I am starting from x and I am moving in the direction of the jth unit vector, and how much am I moving by? I am moving by a step of size hj, right. I am taking a step of size hj, right. So, fi x plus hj ej minus fi of x. So, that's like this is just I am trying to explain what is basically in mathematical terms is known as a directional derivative, right. It is basically a directional derivative, right. So, it is a directional derivative of f in the jth direction, right. It is a directional derivative of f. So, fi x plus hj ej minus fi of x divided by h of j, right. So, that is how, so I am approximating this by its directional derivative, right. Ej is the jth unit vector and hj is the jth component of an n dimensional parameter vector with components hj not equal to 0, j is equal to 1 to n. So, I am thinking of all these h's as one vector, and each component of that vector is a parameter, right, which is less than 1. So, if we let Jxh be the n by n matrix with components Jij which are defined like this. So, these are my components in my J matrix now, and you can see now that now it has become a function not only of x, but also of those h's, right. So, Jij, if we define like that, we get an n dimensional discretized Newton method, right. So, now I am no longer evaluating the exact derivatives, but I am evaluating it like this, right, and but the structure remains the same, Jxkh times xk plus 1 minus xk plus f of xk equal to 0, right. Look at that here, right. So, that was what I had earlier on. The only difference is now instead of evaluating this derivative exactly, I am evaluating it like this, right. So, if we do that, so j of xh can be approximated as, so we can write this as basically, let me go back again. So, I am going to write this as a matrix of these vectors. So, basically it is this, all these vectors, right. So, all these vectors f of x plus h1 e1 minus f of x plus h2 e2 minus f of x, and so on and so forth, right. You can see why that is true, right. So, f1 x1, right. So, that is going to be f1 x plus h1 E1 minus f1 of x by h1, right. So, let us take a look. So, that is f1, so that is going to f1 x plus h1 E1 minus f of x, and then next row will be f2 x plus h1 E1 minus f of x, and the first row, first column will be f1 x plus h2 E2 minus f of x. All those derivatives, for all those partial derivatives I am going to get a term like this, right, and I am taking the, and I have to divide by these h's. So, I am taking those h's outside, right, and writing it as a diagonal matrix. So, this equation is identical, it is just I am writing this equation, right, I am writing it in matrix form, right. If I write it in matrix form, I get f bar times H inverse, right, where H is a diagonal matrix which contains all the h's, all these increment sizes on its diagonal terms, right. Since all these hj's are greater than 0, right, then H inverse always exists. It's a diagonal matrix with non-zero diagonal terms, so its inverse must exist, right. Thus, for the method to work, but remember, what do we have to do? What do we have to do to find my increment? I have to invert this matrix, right. So, to invert this matrix, not only must this inverse exist, right, this be invertible, this must also be invertible. When is that going to be invertible? When it has got full rank. What does full rank mean? That means all these columns, right, all these columns f1 x plus h1 E1 minus f1 x, f2 x plus h1 E1 minus f1 x, and so on and so forth, and this column, all these columns are linearly independent. They are linearly independent. In that case, it is going to have full rank, right. It is going to have full rank, and then this Jacobian is going to be invertible, and it is going to, and my Newton algorithm is going to work. But for this method to work, we have to evaluate this function at n plus 1 points, right. So, you can see all these functions have to be evaluated, right, at each point, right. So, we have to, there are a lot more function evaluations, right. So, this has to be evaluated at xk plus h1 E1, xk plus h2 E2, and so at for any iteration I have to do all these evaluations, right. At any iterate k, I have to do all these function evaluations, right. Function has to be evaluated at all these values. Thus, the amount of if these function evaluations are to evaluate the function is almost as expensive as evaluating these derivatives, then it is not much use, right. Then I can just do my usual full Newton derivatives, right. So, if the amount of computation is comparable to Newton's method, if the evaluation of fi x is as computationally intensive as the computation of this partial derivatives, right. But the question is, how do we calculate the, so we have done, everything works fine, we have seen it works fine so long as these columns are linearly independent and all those hj's are greater than 0. But then what should I take my hj's to be, right. I know that they have to be greater than 0 for it to be invertible, but then how much should that size be? That is, so depending on what I take my hj's to be, I am going to get fast or slow convergence, right. You can assume, you can think that if I take very large steps, right, it is a nonlinear function. If I take very large hj's, then I am not going to get good convergence, right, because the function is varying non-linearly, and if I take very large hj's to estimate my derivatives are not going to be accurate, right. So then what should I use my hj's to be? Well, there can be lots of ways to choose hj's, but one way to choose it is use my the way I choose my hj's for my secant algorithm, right. And what do I choose my hj to be? It is just the previous iterate minus the value of the xjth component of x, the previous iterate value minus the current iterate value, right. So, that is one possible choice of my HJs, right, but depending on how I choose my HJs, I am going to get my rate of convergence is going to be different, right. And if I use my choose my HJs like I do for my secant method, I am going to get the same rate of convergence as my ordinary secant method. Remember that now we can no longer expect to get quadratic convergence. Why? Because we are not using the exact derivatives, right, because we are approximating these derivatives using this sort of directional derivatives, right. So, now we can no longer get quadratic convergence, our order of convergence is going to be less than 2, right, but if we choose the Hj like it is chosen for secant method, then I am assured that I am going to get at least as high a rate of convergence as the secant method, and we saw that the rate of convergence for the secant method was something like 1.6 something, right. So, instead of getting order of convergence equal to 2, I am going to get an order of convergence like 1.6 something, right. Okay. So, we said that we are going to talk in greater detail about ways to solve this equation. On ways to solve, I don't know, where are we? Probably skip that. Anyway, we said that we are going to talk of ways to solve that in that equation, right, this equation basically, not this equation, this equation, right. And so, let us do that, but when we look at ways of solving that equation, it often makes sense to look at particular context, right, because this is as it becomes quite complicated. So, it makes a lot of sense, it is much easier to understand if we look at a physical problem, right. We say that we look at how we solve this equation in the context of a physical problem, right. So, we are going to look at multidimensional Newton algorithm, convergence and things like that in a physical context. And in the civil engineering applications, one commonly encountered context for solving nonlinear equations is when we want to determine the equilibrium configuration of a loaded structure, provided that loaded structure is behaving in a nonlinear fashion, right. My equation in this case, which becomes the equation of motion, right, becomes the equation of motion, or put it more generally, the equation of conservation of momentum, right. That equation is nonlinear, right. That equation is nonlinear. Why is it nonlinear? Well, it can be nonlinear because of several reasons. It can be because my structure has made of a nonlinear material, right, or because I have finite deformations, right. So, my displacement strain relations, I do not want to get too much into the mechanics aspect of things, but there can be lot of reasons why my equation is nonlinear. So, now I want to solve that equilibrium configuration of a loaded structure. So, to do that, we denote the displaced configuration of a structure as x is equal to x0 plus u. Suppose my structure in an initial configuration, it had configuration x0, and then I provide a displacement u, and this gives me my displaced configuration of the structure. So, for that structure to be in equilibrium, it must satisfy this equation f of up is equal to 0, where f of up is my equilibrium equation, and it has variables u, which is basically representing my displacements, but we can think of it as f of x, right, my displaced configuration. But since x0 is a constant, as I am assuming that my initial configuration is known, so I can write it as a function of u, and p, where p is my load vector. So, to solve a nonlinear problem, basically one can think of that as finding the roots of that equation, finding the root of f of up is equal to 0. So, I want to find a displaced configuration and a load which satisfies my equilibrium equation, right. My equilibrium equation is f of u p. So, I want to find the root of that n dimensional nonlinear equation, and what are those roots? The roots are my displacements, and the n dimensional displacement is n vectors, right, n dimensional vector, and my load, which is also an n dimensional vector, right. So, find u and p such that f of u p is equal to 0. So, f is a nonlinear function of the displacements and the loads. It may be nonlinear because of maybe nonlinear material behavior, nonlinear geometry. We do not want to concern ourselves too much with that, but because of some nonlinearity, let us suppose, right. So, if after the findings of f, finding the roots of f of u p is equal to 0, that is after finding the values of u and p that satisfy the equilibrium equation, we plot graphically in n dimensional hyperspace, right. So, we have an n dimensional hyperspace, and for each dimension corresponds to one particular value of u, one component of u, right, and maybe one component of another dimension corresponds to another component of u, another dimension might correspond to one component of p, right. So, I have an n dimensional hyperspace, and in that n dimensional hyperspace I have points. I plot the points, and what are those points? Each point corresponds to a value of u and a value of p, which is a root of my equilibrium equation, right. So, I plot in n dimensional hyperspace all those points, right. In 3D we can points, right, you get a surface, right. So, we get a collection of points that together constitute the entire set of solutions of f of u p is equal to 0, right. So, it is often insightful to discuss algorithms for the iterative solution of f of u p as a series of steps to move from one point in the set of solutions to the next. So, now I have all these points in that n dimensional hyperspace, and the basic problem of solving this nonlinear equation is that given a point, given suppose a starting point, right, given one of those points, one of those infinite number of points, right, given one of those points, how do I move to the next point, right, given one of those points, how do I move to that next point, and what is driving that? Well, one can drive it either by changing the displacements or by changing the loads. If it is a displacement driven problem, I know my initial displacement and my initial load at an initial equilibrium configuration equation, then I change the displacement, right. I change un to un plus delta, right. So, you change my u delta by delta, and then I want to find what is my p, which is going to satisfy f of u p is equal to 0. That is going to be true if it is a displacement driven problem. If it is a load driven problem, it is just the other way around. So, again I have an equilibrium configuration where all my displacements and all my u's and all my p's are known, right, and then I change my load, right, I change my p by delta p, right, and then I want to find what value of u, how must I change u to satisfy the equilibrium equation, right. So, if the independent variables of the problem are the loads p, then the problem is a load controlled problem. If the independent variables are the displacements u, then we have a displacement controlled problem. Let us suppose we have a load controlled problem. Then the problem of advancing from one solution point of the nonlinear equation f u p equal to 0 becomes one of moving from known load and displacement state un pn to the next state un plus 1 pn plus 1, given that pn plus 1 is known. Since it is a load control problem, I know my pn plus 1, I want to find un plus 1 such that my equilibrium equation is satisfied, such that this is satisfied. For the purpose of understanding, it often helps if we consider a two-dimensional idealized problem where the load vector and the displacement vector are treated as single scalars, but purely for illustrative purposes, for just for understanding, right. You keep it in mind that they are not really scalars, they are n dimensional vectors, right. But just for the sake of understanding, let us draw this in PU space, right. Instead of drawing my hyper surface in n dimensional hyperspace, right, which is going to be some strange surface, right, which you cannot even visualize, right. So, if we look at it, if we consider an idealization like this, you can see that this equilibrium solution is going to be, all my points which satisfy equilibrium are going to lie on this red line, right. They are going to lie on this red line. So, what do points on those red line mean? That means at those points my u and p are such that my force, my external force, again this is becoming slightly more mechanics oriented, but let us put it like this, my applied load becomes equal to the system response, right. It is in equilibrium when my applied load becomes equal to my system response. And what is my system response? My system response is a function of my displacements, right. So, given a certain set of displacements, my system responds through what is known as an internal force. It is an internal force which is the system response to my external excitation, right, my external load. And when is the structure going to be when is it going to satisfy equilibrium? When the external response, external excitation or external load becomes equal to the internal response, right. And we are going to represent the internal response by this little function g of u, right. You can think of g of u as the internal response of the system to my external load p, and it is going to be in equilibrium when p is equal to g of u. So, the curve shown in red can be regarded as representing the response of the structure to the applied load. In multi dimensions, it can be thought of as representing the internal force vector g of u. At equilibrium, the internal force must be equal to the external force, right. So, my internal response g of u must be equal to my external load p, which is just writing this previous equation f of u p in slightly modified form. So, if I move p to the other side and then whatever I left becomes g, that is my g. So, that I call my internal force, then this equation I have just rewritten it to be that, right. So, now instead of solving f of u p equal to 0, I am going to solve this equation iteratively, right. So, we are going to get a sequence of nonlinear equations in this form, right. At each iterate, at each step I am going to solve this equation, right. G of u n is equal to f of n, where f of n is my external stimulus, u n n is my system displacement, my independent variable, and g of u n is my system response, right. So, the problem can be restated as given u n and f of n such that g of u n is equal to f of n. So, we start with a state where I satisfy my equation, remember that we start with n, right. So, we know that, and knowing, and since I am looking at load control problems, so suppose I know f n plus 1. So, I know the change in f, right, the change in my external load which has changed from f n to f n plus 1. I want to find u n plus 1 such that g of u n plus 1 is equal to f n plus 1. So, we started with our initial equation f of u p equal to 0, right, and then we just change this to rewrite it in this form, right, because that is easier to solve, right. And next time we are going to look at ways to solve this equation, right. Look at Newton-Raphson, look at conditions under which Newton-Raphson fails, and then we will look at alternative algorithms which can be used under those situations. Thank you.